So I couldn't assign the textbook reading until somebody actually signed up for the course. And I had them have them create it and then send you out the email on how to do it. So if you're assuming everybody's had access to it, they may not have. So one of the things, this is my edited version. So when you look at the learning objectives, you'll see that the ones that I put here in red are the ones that we're going to be going over, and the ones that I prioritize as the most important. Do I want you to be able to learn like linear combination to draw molecular orbital diagrams? We're not doing any of that stuff. So if you did that in your general chemistry class, great. Take physical chemistry and you'll go over it again. But we're not going to do molecular orbital. So these red ones are the big ones that I think. So atomic orbitals are an important topic. So this one I edited last fall. I got through chapter 1 and 2 and then my time just disappeared. So I didn't have time, or I didn't make time to go over. So if we go down here, we will get a problem. There's problem number 1. So problem number 1 is match the elements with the correct valence electron configurations. So that we can't really do by card. Well, we could if it was A through D. But so that's a problem that when you're doing the reading, you're going to answer that question hopefully before you come to class. There is one thing that I should tell you. I cannot set deadlines for fractions of problems in a chapter. It's either all or nothing. And then what happens is when I set the deadline, after the deadline, the problems disappear. And then I have to undo the deadline for you to see them again. So I don't set the deadline. But I will be looking at those problems to just make sure you did them. So I have to do this by hand.
So if we didn't do them.
So if you didn't do them, I would say do them within the next day. And I would say if you get really, really far behind, tell me, and then maybe you do them by the end of the week. But I'll hopefully notice that you haven't had a chance to do them, I might say. So, but this is your way of checking whether you understand something. This is all about practice, right? And take your favorite activity. If you want to be good, you're going to suck at it to begin with, right? This is common educational theory and life theory. When you begin to cook, you're going to suck at it, right? Until you get practice, until you get, to understand what you're doing, you're not going to be a chef from day one, right? Despite unless you get it from the box, I guess, that they send you every week, even with directions, it's going to take a while for you to learn how to cook, do a sport, play an instrument. Organic's no different. We need practice. And practice tells you what you need to ask questions about and what you need to re-practice. So the last thing you want to do is to go into an exam with no practice. I mean, you can do that if you like, but the problem, it may not end up well. So that's why that's why you see in the syllabus, what are the 3 keys? Practice, practice, practice. And ask questions when you don't understand something. All right, so these are the problems. So for question 2, how many unpaired electrons are present in the state? I think you just have to type that one in. Ionic bonding, that's important from the standpoint. We'll go over some of this. So that's what I mean, question 3 here. So there are a number of questions that are embedded within here. And so again, these are participations. You want to do them. You want to get them right? But if you don't get them right, it'll give you a hint. You'll get, I think, 2 chances. But then that's a question you might want to ask me about at the beginning of class. And say, hey, I didn't get that question. I also do have some multiple choice questions on Canvas that we may do in class. That used to be, the idea is if you're gonna do something before class, I want you to do a problem, whether it's an online Canvas problem or, in this case, the top hat problems are what I'm going to want you to do. And there are separate problems that I'm giving you as kind of extra practice. But I can overload you with problems very easily. And no matter if this is all you're doing, you're going to have a hard time doing every single problem. So part of it is to focus on that. Okay, so the general chemistry that's important for organic. The first thing we start with is Lewis dot structures. And so what do? You think back to your second semester, probably second semester general chemistry. What topics did you talk about? First, you talked about drawing Lewis dot structures. Then you moved into Vesper theory to determine geometries. Then after the geometries, what came next? Intermolecular forces. You may or may not have talked about hybridization. And organic hybridization we're going to talk about because we're doing things with carbon and oxygen, nitrogen, so we need to understand the hybridization, and we'll do that today. So, if we're looking at drawing Lewis dot structures, and we'll get to electronegativity here in a minute as well. So how do we draw Lewis dot structures? Well, here are some rules to help you do that. Typically, if I'm going to give you a Lewis dot structure to draw, I'm going to give you I'm going to give you how the atoms are connected. And then I'm going to ask you, okay, fill in the bonds, the lone pairs, etc. So if we wanted to do a problem here, let me insert a new slide, several new slides. So let's say we wanted to draw the Lewis dot structure of something like nitric acid. So you may have seen in the past HNO3. I'm going to basically say, okay, what's the central atom here? On that slide it says typically the atom that's the central atom is going to be the least electronegative one. And so with the periodic table, which is in sad shape, but I have a brand new one that I'm going to put up this afternoon. What's the most electronegative element on the periodic table? Fluorine. So everything moves towards fluorine. If you're going left to right, electronegativity increases. If you go from bottom to top, electronegativity increases. So if you just think about fluorine as the most electronegative element, everything moves towards fluorine. And so that makes it a little bit easier instead of trying to so what happens when you get that. So that's how everything's moving. So in this case, what's my central atom going to be? It's really down to nitrogen and oxygen. Which one is least electronegative? Nitrogen. And usually when I ask questions, feel free to jump in. Particularly if there's a long pause between me asking the question, a lot of silence, that's not a rhetorical question. Usually rhetorical questions, I'll answer right away. So, we've got an N, 3 O's, and then hydrogen, I would basically say the hydrogen is going to be attached to one of the O's. If you've done Lewis dot structures, you're on your own. I'm going to give you the skeleton. Now, when I give you the skeleton, we do not draw rings right now. So no triangles, no squares, no pentagons, no hexagons right now. We will in the future. Okay. So the next thing, what should we do? What I like to do is to give each atom its valence number of electrons, or the Lewis dot structure with its valence number. So for nitrogen, since nitrogen is group 5, it's going to get 5 valence electrons, so 1, 2, 3, 4, 5. Oxygens all have 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then hydrogen has 1. So this is the way I like to do it. I know other people say take the total number of electrons and start distributing them around, which is okay. But I like to sort of give each atom its own numbers, and then we can move them around. If I wanted to pick up an electron from the oxygen and give it to another oxygen, that's okay. Just don't lose it. Or don't have it become 2 when you put it back in. Okay. If I have a positive or a negative charged ion, I need to either erase an electron from anywhere or add an electron anywhere. Okay. So next thing I should do is I'm going to create the single bonds. So I'm going to take an unpaired electron here. I'm going to share those 2. I'm going to share those 2. I'm going to share those 2. And I'm going to share those 2. Can I share 1 with one of a pair? Yeah. And so what would be next then? Next, I probably want to make sure that each atom has an octet, no more, no less, if possible. Hydrogen only has 2, so it's good. This oxygen right here has 6. We'll leave it alone for the moment. The nitrogen has 2, 4, 6, 8. It's okay for the moment. But these 2 oxygens, they have 2, 4, 6, 7. So that's a total number they share. And so I need to make that 8. And I need to make the other oxygen 8. So any suggestions as to what I should do? Okay, so I could say I'm going to do a double bond there. So that's going to give me this. Should I draw a double bond to the nitrogen to the other oxygen? No. Why not? Then nitrogen has more than 8. Can nitrogen have more than 8? No. What elements on the periodic table can have more than 8 valence electrons? Sulfur is 1. Phosphorus is 1. We're going to find out third row and lower can have expanded, what we call expanded octets. So third row and lower. Why is that? Well, actually, if you've never heard the reason for that, I'll talk about that in a minute or two. So third row and lower can have expanded octets. Nitrogen, carbon, oxygen, not third row. So they cannot have expanded octets. As a matter of fact, let's see. We have a series of things not to do. Biggest mistakes in organic chemistry. I only have 3 of these. If I had 10, I'd sell a t-shirt. Number 1, taking organic chemistry. And no choice in that. Number 2, 5 bonds to carbon. 5 bonds to oxygen. 5 bonds to nitrogen. Second biggest mistake. We'll come to the third and maybe fourth later. So, I can't form a double bond. What should I do? Right now, nitrogen has 2, 4, 6, 8, 9, so it needs to get rid of 1. How about I erase this one and bring it down here. This oxygen was short one, the nitrogen had an extra one. I'll just move that electron down there. If you don't like that, we'll pick it up and move it there. And are we good with that? All the atoms have expanded, or have octets, only octets, no expanded octets, and it looks like that is a legitimate. That looks like that is a legitimate Lewis dot structure. Now, whenever we have a Lewis dot structure, the next thing we need to do is to assign the formal charges. So when we're talking about formal charges, there is a formula you can use. The formula is the number of electrons in the neutral atom minus the number of lone pair electrons minus 1/2 of the bonding electrons. That's the formula that you can use to calculate the formal charge for each atom. Personally, I use a more qualitative approach. When the atom came to build the molecule, it brought a number of electrons. So nitrogen brought 5, oxygen brought 6, hydrogen brought 1. In the end, the nitrogens and oxygens share 8. But how many do they own? Okay. So everybody shares 8. How many do they own? Well, we're going to assume that if the nitrogen and the bottom oxygen here, if these nitrogens were to split, that they're going to split equitably. So that bond, 1 electron will go to nitrogen, 1 electron will go to the oxygen. Okay. And if we assume that, then that means that nitrogen owns 1 electron and the oxygen owns 1 electron. So what would be the formal charge of nitrogen? I'll give you a minute. So what's the formal charge on the nitrogen? Actually, what's the formal charge on all of those atoms? Nitrogen, oxygen, not hydrogen. Well, why don't you take a minute and write the formal charges for those, and then we'll use the cards and I'll ask you. So in other words, so that formula, what it means is that if you have a lone pair, that does automatically go to the atom. And so, for instance, the OH bond, that's 2 bonding electrons. That's 2 electrons in that bond. So 1/2 of that means that the oxygen. In the future, we'll probably do the group up so that you guys can talk. Educational theory says that's the interaction. It's called active learning. I'm supposed to not talk. You're supposed to do a lot of active. That's what we're probably thinking. So does everybody have the nitrogens? Formal charge? So we can let's start with the nitrogen. And so your choices are 0 is A, +1 is B, -1 is C, and -2 is D. And if your number is not on that list, you might need a new number. Okay, so let's see what we have. So you just hold the thing up, you hold your card up with the correct, or with whatever you think is. So whatever's on top, that letter on top is the okay, and then I hit the button, and it's supposed to graph. There's the graph. Okay, so we have 7 B's, looks like. So nitrogen has a +1 charge. Okay. So that's going to be +1 on the nitrogen. Now how did you get that? Let me start. So nitrogen has 5 electrons in the neutral nitrogen atom. So it brought 5. How many does it now own? It owns 1 on the single bond to oxygen, 1 on the other single bond, so that's 2. It owns 1 here and 1 there. So it has 4 single bonds, so if you want to think about the formula, that's 8 bonding electrons. It owns half of those. But it owns 1 bond, 1 electron in each one of those bonds. So nitrogen owned 4. So that means for the nitrogen, it started with 5. It now owns 4. That means its charge is +1. Yeah.
So if you want to count the bonding electrons, you are not just counting the bond as 1 the bond as 2.
Yes, I'm counting the bond as 2.
And then when you count the unpaired, you are just counting.
Right, so this is the lone pairs and this is the bonds. So the lone pairs go all to that atom, and the bonding electron and the bonds go 1 each.
So the bonds.
Yes. Right, so each bond is worth 2 electrons. And what I just showed you was 2 different ways to do it. You can use the formula, or you can use a less mathematical. So that, and there's probably other formulas out there. So looking then at this oxygen right here, what is it? So what is the oxygen's form? That oxygen that's circled formal charge. Okay. The view. Okay, so we have 7 C's. So -1. So that oxygen, so this oxygen now has, it's got all 6 lone pairs. So lone pair counts as 2 as well. So it's got 6 in the lone pairs, and then it's got half of the bonding pairs. So it owns 2, 4, 6, 7. Oxygen only came with 6, and so it came with 6. It's now got 7. That means it's got an extra electron, which gives it a -1 charge. And the other 2 oxygens, what's their charge? They're 0. So for this oxygen right here, it owns 1, 2, 3, 4, 5, 6. So it owns 6, it came with 6, no net change. So the key is this is step 1. Drawing the Lewis dot structure, and then being able to write the formula, and then being able to write all the formal charges. And you guys probably spent what? 3 lectures, a couple lectures on that in General Chem, maybe a week on Lewis dot structures. Yeah, 20 minutes. Maybe an entire lecture period looking at it. So we're going to go through about a month of general chemistry, like just this morning. That's why I'm hoping it's review, and if it's not, then hopefully we're all at the same page. So, is that to refresh the memory? So our formal charges then, this is another slide. So here's the formula. Number of electrons in the neutral atom minus 1/2 the bonding electrons, and then minus the number of unpaired. And the sum of the formal charges has to equal the overall charge in the molecule. In this case, that was a 0. It was a neutral molecule, so the formal charges have to add up to 0. If they don't, you got something wrong. We'll come back to that structure in a minute. Because now, what we can talk about is that the only possible structure of nitric acid? So this is what we have now. So that's our Lewis dot structure. Is there another one that I could draw? Now, I'm gonna have to enforce some rules here. You are not allowed to break any bonds, make any new bonds, other than maybe a double bond. So you're not allowed to break the sigma bond, single bond structure of the molecule. You're not allowed to move atoms. So if I was to draw another Lewis dot structure, it needs to look like this. None of the atoms can be moved. The only atoms, and I already put in the single bonds, I can't move the single bonds. Maybe I can move lone pairs, maybe I can move multiple bonds, but that core structure has to be the same. So what other structure could I draw? Okay, so if I draw the double bond there, then how many lone pairs should that oxygen have? How many lone pairs should each of the oxygens have? 2. Top one should have 3. And this oxygen over on the right, we all agreed that we didn't do anything to it. So the oxygen on the right is going to stay the same. Now you might say, well, how did I know where to move the electrons around? So is there a way I can show how to get from the left structure to the right structure? So let's do this. Let's take this lone pair and let's use it to form the double bond, to form the nitrogen-oxygen double bond. Now if I do that, can I stop there? No, I can't. Because if I stop there, I would have this structure if I just move that lone pair of electrons between the nitrogen and the oxygen, I have that structure. What's wrong with that structure? The nitrogen has how many, it's sharing how many valence electrons? 10. Is it allowed to do that? No. So I cannot stop there. This is not allowed. So if I move this pair of electrons to form the double bond here, I have to take this pair of electrons and move it out and give it to the oxygen. And if I do that, I've now turned the left-hand structure into the right-hand structure. And those two structures would then be called resonance structures. Those are resonance structures. And what goes between resonance structures is a double-headed single arrow. So those are our two resonance structures. Now I'll go back here because the formal definition of resonance structures we need to refresh. And there's some rules of resonance that we always need to follow. Okay, so those are the two resonance structures for nitric acid. Now, let's go back to the rules of resonance. Right, resonance structures are imaginary. We come to the resonance hybrid here in a minute. But resonance structures, resonance forms, or resonance structures, number 2, differ from each other only in the placement of their pi or non-bonding electrons. Pi means multiple bonds, this double and the triple bond. Different resonance forms don't have to be equivalent. One may be more stable than the other, and the most stable forms will contribute to the resonance hybrid. We'll go to that in a moment. All resonance structures must obey the normal rules of valency. That is important. Every resonance structure cannot have an expanded octet if that atom cannot have an expanded octet. So you can't break the rules of valency when you're drawing different resonance structures. And so let's go back to the idea of number 1 here. Resonance forms are imaginary and not real. So if we go back to our nitric acid example, what is the real structure of nitric acid? It is not number A, it is not number B. It is not the left-hand structure, it is not the right-hand structure. It is what we call the hybrid, the average, right? So in the early days of resonance theory, people did believe that those two structures were constantly flipping back and forth. And that came from the benzene ring A benzene ring has 6-membered ring of carbons, and there's 2 ways to draw that with the double bonds in different places. The intersection between those lines are carbon atoms, and then there's 1 hydrogen attached to each of the carbon. So in the early days, when the benzene ring structure was proposed, people thought that those 2 benzene rings flip back and forth really fast. But here's my totally absurd example on resonance structures in the hybrid. So A and B are not going to exist discretely and flip back and forth. It would be like if I had a Chihuahua and a Pit Bull, and they bred. The resulting dog is not going to be constantly flipping back and forth between a Chihuahua and a Pit Bull. That would be kind of cool, but it doesn't happen. So it's kind of like genetics and biology. We have a hybrid. We have an average. Although on the Super Bowl commercial a few years ago, they had this Doberman Chihuahua thing running after a Kia or a Hyundai or something like that. It was a Dobrahua, I think they called it, with a big Doberman head, the Chihuahua body. That doesn't happen either. I thought they kind of ripped off my example. So the hybrid is the average. So what's the hybrid going to be? Well, let me erase these benzene rings. So the first thing in writing the hybrid is to write all of the atoms with the single bonds in place. That's the first step in writing the hybrid. Because single bonds I can't break, I can't move atoms. So it's automatically going to look like that. Now I'm going to average the bonds and the charges. And this is the weird thing about hybrids. We only average charges and bonds. The number of electrons are not shown, but they are because the lone pairs give you the charge. So let's start with the oxygen on the right. 0 formal charge, 0 formal charge, 0 formal charge. The nitrogen, what did we have? We had what? +1 and then +1. So what's its average? +1. Do I have to show that? Yes. Okay, so the nitrogen has an average of +1. Now, for the top oxygen, you're going to learn very quickly that an oxygen with a double bond and 2 lone pairs is 0. An oxygen with a single bond and 3 lone pairs is always -1. So the top oxygen has a 0 -1. What's its average? You could say -1/2. I don't care about the details. Because this one, it is -1/2. But in the future, we don't know. And we'll get to that in a minute. So in this case, I'm going to say, you know what, that oxygen, it has some negative charge, and we use the delta term in chemistry to indicate partial. So that oxygen has a partial negative charge. It's somewhere between 0 and -1, the exact number I don't know. And then what about the bottom oxygen? Same thing. It's got a -1 charge here, a 0 charge there. It's going to be delta minus as well. So that -1 charge, because the nitrogen is +1, that -1 charge is split up between those 2 oxygens. And actually, since the 2 resonance structures at the top, A and B, have basically the same charges and bonds, it's just there's a symmetry to it, they will end up -1/2. But in the future, we're just going to say, oh, that -1 charge is split between those 2 oxygens. It's being delocalized. And then the nitrogen with the +1. Now it's average bonds. So oxygen, hydrogen, single bond, single bond, single bond. NO to the right, single bond, single bond, single bond. Top, oxygen, single bond, double bond. What does that mean? The bond's somewhere between a single and a double bond. We give it a partial bond, so a dotted line means a partial bond. And then the bottom NO bond, partial double bond as well. Physically, what does that mean? That means that bond is somewhere between a single and a double bond in length. Single bonds are longer than double bonds, which are longer than triple bonds. So that NO bond is going to be somewhere between a long single bond and a shorter double bond. And that's physically how we would know that that's what the true structure is. That those bond lengths would be exactly the same. So that's how we write the structure of the resonance hybrid. And that's the true structure. Now, there are going to be times this semester when what we do is we just basically will react each individual resonance structure because it's easier. But really, it's the hybrid that's the true structure. Always the true structure. All right, so you kind of okay with that? I mean, we need some problems here, which we'll get to. So all those rules of resonance go into that. Many books don't necessarily have these laid out. I like to lay them out. You may even see them in the textbook because I think in chapter 1 I got a chance to cut and paste those in. Okay. All right, so what happens if we don't have resonance structures that are the same? And I have to define, what do I mean by the same? Well, here we're not talking about same structure because you might say for those two that we wrote on top there, two resonance structures, you might say, well, they have the same structure. All I need to do is take my structure and flip it. Except that violates the rules of resonance because you're not allowed to move atoms. So it's as if the top oxygen is oxygen A, the bottom is B, and the one on the right is C. I can't interchange A into B. So all I'm moving are pairs of electrons, the atoms are stuck. So while we look at the top two and we say, they're identical, what are they identical in? They're identical in energy, they're identical in stability. Because they have the same bonding scheme, the same formal charges. Although what's going to be important is not the bonds, but the charges. So, here's N bonded to N bonded to O. Although the better one would be, let me just change this up. That's not erasing. I like NCO better. So NCO minus. So for our NCO minus, draw a legitimate resonance structure for NCO. And by legitimate, what I mean is, you didn't violate the octet rule, and all the formal charges add up to -1. All you got to do is draw one.
If you get one drawing, you can go ahead and try and draw as many as you can. Make sure you don't have any standoff heads. Anything probably with less than an octet. Not good. Then you know, then you have stuff moving and start having that movie.
Now, remember, since this is a -1 charge, what do you have to do? Well, but in terms of putting all the electrons in, you need to add one additional electron to the molecule to make sure it's a negative electron. So if you have like an unpaired electron, you need to add one more to it, or take that one away, whichever. Because for a neutral one, you don't have to add anything, -1, you need to add one electron, +1 overall, you need to take an electron away.
You can put it anywhere you want.
So you want to put, when you get your structure together, put your formal charges on the atoms. Yes. There might be, there's one. It's okay.
The idea here is that if we all have one, we'll get all three of them.
But you know how here we took the electron and we kind of moved it? You can use that approach to make another, to make them. They all should be able to be converted back and forth.
And if you're watching this, hopefully you're doing this at home too. There's hopefully 2 people that are watching it. 3 actually. Wait, do we all have at least one? Okay. The other thing I don't have is I don't have all of your names loaded into my iPad so that I can push a button and randomly choose people so that I'm not constantly choosing one person and ruining their psyche. But I don't have that today. So, who wants to volunteer a structure? Eleanor. It's only 12 names. Most of the 60 from last semester are gone. Not all of them. But the quicker I know your name, we're not putting tents out, full tent name cards. Okay, tell me, Eleanor, what you want to do. For nitrogen, how many lone pairs? 2 lone pairs, nitrogen, carbon, single, double, triple, carbon-oxygen bond, oxygen, 2 lone pairs. Formal charges, non-zero formal charges. -1 on nitrogen. Okay? Do we see anything wrong with that? No violations of the octet rule. The formal charge is correct. Formal charges add up to -1. Legitimate structure? Yes. Okay, does anybody have anything different? And Mel.
Yes. So you had triple bond.
How many lone pairs on the nitrogen? And formal charge? Okay. Is that one okay? All right, no violations of the octet rule. Formal charges are correct. Everything adds up to what it should. Okay, does anybody have a third one that's different? Alex.
Okay, so you had triple bond between the carbon and oxygen. There's single bond between the
How many lone pairs on the nitrogen? And how many on the oxygen? Okay. Formal charges.
the carbon is -2, carbon is 0, oxygen is
Okay. Okay, we've got 3. And that's all there legitimately is. With the rule that everything has to have an octet and no expanded octets. So we've got 3, A, B, and C. So let me ask you a question. Before we go over the rules, because the question is going to be, do these 3 have the same energy? And the answer is no. They don't. But the question that I would like to ask is, of those 3, is there one that you think would be the most unstable? The most unstable of the 3. And I know we haven't gone through the rules yet, so if you have to guess, what does your gut tell you? One of these is less stable than the other 2. Say that for a fact. Which one do you think it is? A, B, or C? And it's okay if you're wrong, that's fine. Because this is just a gut instinct. So which one of those 3 do you think is the least stable of all? And you could use D for, I don't know. And then we're all playing along. So which one is the most unstable? A, B, C, or I don't know. D. think you just got to move your hand a little bit. There. Okay? Okay. I've got 7 C's, 1 B, 1 C, and 1 D. Somebody's honest, they don't know. It's fine. One of the 7 people who said that they thought C was the most unstable, why did you think that it's the most unstable?
I just kind of vaguely remember, like, if there's more changes in depending on the formal charge, how those like -2 and just +1, as opposed to just the -1 on one of the atoms. If like both of them are neutralizing, it's like slightly more unstable.
Okay. What was another reason? If that's the same reason, you could say it the way you think, or what you think.
I was just saying, so just more neutral
Okay, so 2 formal charges versus 1 formal charge. Seems like that makes it more unstable. How about the charges themselves? -2. It's probably not going to be very good for the structure if it's a high number versus a low number.
So, if the formal charges are like higher or lower, that would be more.
That's what we're going to find out. So I heard 2 things there, and hopefully, if you have anything else to add, feel free. So I heard the number of charges that were not 0 is important, and the size of the charge, which I probably added myself, is important. And C has what? It's got both of those going for it. Remember, those are not good characteristics of being stable. So now let's go back here and let's talk about the rules. So here are the rules, and they are in order of importance. So in other words, we use these as tiebreakers. Number 1 can break a tie. Number 2, then if they're the same, we go to number 2. If they're the same, we go to number 3. Each atom should have a completed octet. Does that rule out any of the 3 that we drew? No, they all have octets, right? So they all pass number 1. Number 2, they should have 0 formal charges or small formal charges. I've said 0 would be best, +1, -1 versus +2, -2. So number 2 says which one is the least stable. Because they should be small, -1, ±1 versus ±2. The -2 on number C does what? That makes it less stable. So we can go back to number C, and we can say, well, according to rule number 2, that should be the least stable of all. Yes?
Is there anything that to do with stability in the bonds?
That's the weird thing, no. Now, the bonds play a role in the charges, but not the bonds themselves. When we look at the stability of resonance structures, we're only looking at charges, not the bonds.
So there's no preference for two double bonds or either.
If there is a preference, it's going to be because the charges that result from that bonding. So that's kind of weird. The bonds don't play a direct role, they only play a role in the charges. Okay, so we got number 3, but what about A and B here? They both have a -1, so as far as we're concerned, they're tied. So in rule number 2, they're tied, so now we need to go to rule number 3.
Rule number 3 says that the formal charges should agree with the electronegativity. What is that?
I was just doing it last
Which kind of charge?
time.
Okay, so the formal charges and the electronegativity have to match up. So it's going to depend on the charge. So what kind of, if I have an atom that's more electronegative than another, what charge do I want to put on that? I want the negative charges to go with the more electronegative atoms, and I want the positive charges to go with the less electronegative atoms. So in this case, we're down to 2. And the question is, for A and B, I've got a -1 charge on nitrogen, a -1 charge on oxygen. Who wants the negative charge? The oxygen. Why? Because it's more electronegative, looking at the periodic table, and you will always have a periodic table to work from, whether it's in here or whether it's on a piece of paper in front of you. Oxygen, more electronegative than nitrogen. So in this case, B is going to be more stable. It will have the number 1 stability, and the nitrogen will have the number 2 stability. And so your question about the bonds, they don't come into effect. So that's what's kind of weird. You would expect, well, maybe A is more stable because it's more symmetrical with the 2 double bonds. No. That oxygen wants more electronegativity than nitrogen. Now, how much? I don't care, honestly. And if I wanted to know that, I'm going to have to go to the computer and figure that out. Because this is not a simple calculation you can do in your head. But I do know this. I know that the oxygen's probably going to have more negative charge than the nitrogen, but guess what? Well, we can't guess what yet. Does that make sense? I'm not supposed to ask that. I'm not supposed to say, does that make sense? Everybody nods their head. I'm supposed to give you a problem to make sure that it makes sense. But I still will ask that question. So let's see, what do we need to do next? We need to write the resonance hybrid. Now, are we going to average all 3? If we average all 3, it's going to look more like, I don't know, number 2. So usually in this case, I will say average the 2 most stable. So you know what? Number C is really unstable. It's not, well, okay. When we're looking at the resonance hybrid, can't get too far ahead of myself. In the rules of resonance, it said that structures don't necessarily have to have the same number sheet. And so A, B, and C in this case, they all have distinctly different energies. And those energies are kind of the weighting factor of what goes into the final resonance hybrid. And you know what the weighting factor is. Maybe it's as simple as this class. You get 100% on all the quizzes. You're not going to get an A necessarily, right? Because that's low value. You get 100% on all the exams. You'll probably get an A because that's a higher percentage. So those are the weighting factors for the grades. The weighting factors for contributing to the hybrid are the energies. And again, I don't know those exactly. I don't care about them exactly. And if I do, I gotta do a lot of work for it. So 1 and 2 are going to contribute more to the hybrid than 3. Why? Because 3 is less stable. A little bit will contribute, but let's just ignore that to make the math easy.
Right? So write the resonance hybrid for 1 and 2. So what does the resonance hybrid look like?
So every time it goes from this,
If there's more than 2. So what you'll find is if I give you a couple of these problems, which I may do tomorrow, like Thursday or something, there are going to be times when I have 3 and one is really less stable than everything else. And so I'm going to say, just do the top 2. So I got to tell you, otherwise if we average those out, it's going to be a mess, right? Because what did I say? I said the oxygen is going to have most of the negative charge, but if I averaged all 3 of those, +1, -1, that means oxygen is 0. That just contradicts this. But not if this is only contributing like 2%.
So if I was to write the resonance hybrid, I'm going to start with single bonds. I'm going to average charges and average the bonds. So starting with nitrogen, what's its partial, or what is its charge going to be? Slightly negative, partially negative, delta minus. Because nitrogen goes from -1, 0, average, delta minus. The carbon charge, 0. Oxygen charge, delta minus. Okay, for bonds, just for number 1 and 2, the nitrogen is going to have what bonding? So it's going to be a partial triple bond, is the way we would say that. It's a double bond and a triple bond. The average is 2.5 bonds, and more between a double and triple bond. And then for the NO bond, it's going to have a partial double bond. So that's going to be the resonance hybrid. You'll see in some of the notes that I draw, we usually put a bracket around the resonance hybrid to show that that's the resonance hybrid. And if I was really concerned about, okay, the -1 charge is going to be split between the nitrogen and the oxygen, who's going to get more? Oxygen's going to get a little bit more. How much? Don't care. What I really care about is the fact that the -1 charge is split between the 2. And I don't need to know which one is more or less, but I know since number B was more stable, there's going to be a little bit more negative charge on the oxygen. And I know that because oxygen is more like the negative. How many weeks of general chemistry was that? At least 1, right? Lewis dot structures, resonance structures, hybrids. It's now been 9 years since I taught general chemistry last. And then it was 10 years before that. But I used to teach organic and general chemistry. My first 6 years I taught both of them, which means some lucky students had me for 2 full years of chemistry. Lucky, unlucky, it's probably up to them. But I still remember what goes on in general. Now, why am I concerned about this for organic? The relevance here for organic is going to be that we are going to be drawing resonance structures because some molecules are going to react with one atom or the other, and that's going to depend on which resonance structure is the most stable. So this is just kind of our review of that. Okay. So, because I went on about the syllabus and the structure of the class, let's take a 5-minute break or so. We're going to take a break in the morning. 2.5 hours is brutal. mean, I've been up here walking around and everything. I usually am sitting at the desk writing on here. I don't know how much. Yeah, well, I guess this is my workout for today. So let's take 5 minutes and then we'll start back at 40 if you need to. So the layout of this floor, since most of you don't necessarily know it, but you were able to find the room, which is good. The restrooms are up straight, and the drinking fountain is over all the way at the end of the hall to the left, if you need to find either one of those. It's straight up to the right. Okay, so part 2. Part 2 is going to be a different. All right, so what have we done? Sometimes I do this just for my own thinking. So Lewis structures take us to, resonance structures take us to the resonance hybrid. What else do we need to talk about? What would come next? What would come next is a mixture of Vesper and hybridization. And I'm going to kind of mix these two together. So, oh, this is a PowerPoint. Beautiful. Because it's one page. It's your big note. It's the one, it's the note that is just one single PowerPoint. So when we draw a structure, when we have a Lewis dot structure, that's great, but it doesn't tell us what the shape of the molecule is. And organic chemistry is really kind of about shapes. And we'll get to that because it's so intricate a shape that if you had a molecule that's like a left-hand version and a right-hand version, they'll be mirror images of each other, but they'll react completely different with other molecules that are mirror images. And this is all about drug chemistry. So for instance, there's like molecule dopa of dopamine that if it's in the wrong-handed form, it doesn't work. And then there's drugs like thalidomide that was given to pregnant women in the 60s, where one of the handed forms was a sedative and the other one caused really terrible birth defects. And so they had to separate those two forms out. And actually it's like the number 15 drug that's sold in the US, which if I was a drug company, I would never sell that. The risk is too high. And the consequences are incredibly bad. So when we're talking about getting to shapes, that didn't print out. That page didn't print out. Oh, sorry. Well, all this stuff is online too. So let's just quickly go through the guidelines. So before I can get a shape, I need a legitimate resonance structure, or I need a legitimate Lewis dot structure. I don't think I can write here. No, I can't. So I'll come back. How do you do that? Number one, get the correct Lewis dot structure. We're not going to be doing molecules with resonance structures, but in theory, the shape of the molecule doesn't depend on resonance structure. They all have the same shape. They're better, or else they violate the rules of resonance. And then we count the total number of electron pairs, treating a double or a triple bond as if it was one pair of electrons. And we'll find the reason why. Then we use the tables shown earlier, which I'm not quite sure where those are shown earlier, so we'll develop them here. And that's going to predict the geometry. And then we're not going to be too concerned about exact bond angles, but this is where like the bond angle in water is 105 degrees instead of 109.5 because of the squishing that happens because of the lone pairs. So these are the guidelines that we're going to use to write our Vesper structures, and integrated in those is how we look at this at a really lower or at a higher level in terms of how do we really form a carbon-carbon bond, and that's going to involve hybridization. Right? So let's go back here and let's talk about we'll talk about hybridization, but before that we'll talk about the all right, so now let's do not the video. Let's look at this. Let's look at the hybridization, and we'll draw that out. So what we have to do is we have to imagine that the bonds between atoms are big balloons with negative charges. And negative charges love to repel each other. And so when they repel each other, that's what sets up the geometry. So let me go to the end here and add a couple of blank slides. So when we have an atom that just has two single bonds to it, we can treat those two single bonds as if they were big balloons of negative charge. If you have two balloons that are repelling each other, what geometry do they take? They take a linear geometry, because they're as far away from each other as they can get, and that sets up the bond angle here of 180 degrees. If we now take an atom and we have three bonds, and those bonds can be single bonds or double bonds, it doesn't matter, we're treating them all the same, then what we have is we have a 120 degree bond angle, and all three of those bonds are in the same plane, so this is what's called trigonal planar. This is what's called linear. So we have linear, trigonal planar. Then when we go to four bonds to an atom, we have what's called tetrahedral. And there the bonds are 109.5 degrees, because that's what the bonding angle is for the four corners of a tetrahedron. And if you say, well, okay, carbon, nitrogen, oxygen can only form four bonds, we should stop there. Let's go a little bit further, because we will have some atoms that can go expanded octets. So if you have five, they adopt that geometry, which is trigonal bipyramidal. And here you've got a 120 degree bond angle with a 90 degree bond angle. So take a linear and a trigonal planar and put them together, and you get trigonal bipyramidal. And then finally, if you have six, you have octahedral, which then has 90 degrees. It looks like an XYZ coordinates. So in terms of determining the Vesper geometry, and Vesper means it's not even Vesper, it's valence shell electron pair repulsion. So that takes into account the fact that all these bonds are huge clouds of negative charge. I don't know where my balloon picture is, but I have all of these with balloons, and they're all pushing away from each other. That's what sets up the geometry in general chemistry. That's what sets up the geometry. So we'll do a couple examples here, but what I want to do is I want to relate this to carbon. Because, okay, this is great. This is a simplification. So you can have a carbon that'll be linear, a carbon that'll be trigonal planar, a carbon that'll be tetrahedral. Even in the future, carbon that'll be trigonal bipyramidal. But then you're going to say, how do you violate the octet rule? We don't. 2 of the bonds are half bonds. But we'll get there in about 5 days. Normally I'd say that we get there in a month, but it's fast. Right, so let's go back to the top here. So, oversimplification of bonding. Well, our first oversimplification was taking 2 dots and drawing a line. What does that mean? Typically what that means is that we have 2 atoms that are made up of a nucleus and valence electrons, which the valence electrons are outside. And what happens is the positive nucleus is attracted simultaneously to both of the electrons when we form a bond, and that's what the sharing term means. So those valence electrons are simultaneously attracted to those 2 nuclei. That's even more detail about what a chemical bond is. Then we can go even further in general chemistry, and this is probably first semester general chemistry, so that's even farther in the past. But then we can talk about the wave functions, and it's an overlap of wave functions to give us the bond. So if we do that, then we have to remember that hydrogen is made up of 1s. It has a 1s electron, so it's a spherical, that's what S stands for. And so we're going to overlap those 2 spheres with wave functions, the mathematics of how the electrons move, and we're going to make our hydrogen-hydrogen single bond. Okay. And so that is even more detail. Then we can say, okay, remember that s orbitals are spherical, and the farther they get away from, the farther the valence electrons get away from the nucleus, the bigger the sphere. And what tells us how far away the electrons are? That's the number, the row number. And then we have p orbitals, and p orbitals are dumbbell-shaped orbitals that can be oriented in the x, y, or z plane. There is a nodal plane between them. So in other words, somehow the electron gets from one lobe to the other without ever stopping at the plane between those 2. That's a quantum mechanical thing that we're not going to get into, how they move without ever stopping there. Don't need to know that. I couldn't explain it to you even if I wanted to. And so what happens, we bring those 2 s orbitals together and we get a hydrogen. So, let me tell you the story about methane. So methane is CH4. It's the simplest organic molecule. It's what's in natural gas. Comes out of both ends of a cow. We'll leave it at that. So methane is CH4. What's known experimentally is that all 4 of the CH bonds are exactly the same. The molecule is completely symmetrical. So question number 1 that we have to deal with is, if I'm going to take a higher look here at forming those orbitals, forming those bonds from the orbitals, I get a problem. My problem is that the ground state electronic configuration of carbon is 1s2, 2s2, 2p2. But we know that when you draw the Lewis dot structure of carbon, you draw 4 unpaired electrons. Well, that's not the ground state electronic configuration. So what happens? What happens is you apply a little bit of energy to carbon, you take this electron, one of those electrons, you unpair it and you move it up there to the empty 2p orbital. And now you get an excited state. So now what we end up with is, now we end up with 4 unpaired electrons. The core electrons are never used in bonding in this class. So we've got S, so now we've got one S and three P's. Each orbital has an electron. Okay. One S, not going to bond. That's why carbon can't have 5 bonds. Although, if you could get those 1s electrons to bond to something, you will win the Nobel Prize. Well, somebody already did. They made CH5+, and they won the Nobel Prize. There's George Orwell when he was at Case. He used a superacid to protonate methane, and subsequently won the Nobel Prize. So since we're only interested in getting organic through and not winning any Nobel Prizes, we're just going to leave it at 4. So my first problem is now solved. I now have 4 unpaired electrons to bond with hydrogen. So now I'm going to take my hydrogens and I'm going to say, okay, I'm going to bond the 3p orbitals with the carbon with hydrogen 1s, and I'm going to do the same thing with the 2s. And so now I'm going to make my CH4, except I now have a second problem. My second problem is, of those 4 bonds, one comes from 2 spherical orbitals overlapping, and the other 3 come from a dumbbell-shaped orbital overlapping with a spherical orbital. Well, if that was truly the case, would methane be symmetric? No. But I said at the beginning that methane is symmetric. So problem number 1 solved. I've got 4 unpaired electrons. Problem number 2 not solved, because I have a symmetrical methane molecule, but I have orbitals that aren't symmetric. So if you're working on solving this problem, then the next thing you do is be creative and say, how about I mix the S and the P's all together and make 4 identical orbitals? 4 hybrid orbitals, right? So, I mean, just like we made hybrid resonance hybrids, now let's make hybrid orbitals. Okay, so if we do that, if we mix the 2s, if we mix the 2s and the 2p orbitals, and I'm mixing the orbitals, no electrons yet, I'm just mixing the orbitals, I'm going to end up with 4 sp3 hybrid orbitals. And what's going to happen is, which we now know, that one of the lobes is big and one of the lobes is small. The small lobes, there's going to be times when I'm going to come back and say, remember that small lobe? We're going to use it. But maybe not so much. So I'm going to make 4 orbitals, 4 clouds of electron density. So, what geometry should it have? If it's got 4, if I got 4 balloons, what geometry will be around that carbon? Tetrahedral. So it's going to be a tetrahedral geometry, and it's going to look like that. Okay, the small lobes aren't shown here. So what I just did was I just mixed my empty orbitals, and I made 4 hybrid orbitals that are exactly the same. Problem number 2 solved. And there's the one that shows the little teeny tiny orbitals. And all of these are online. So if you want to go back and print out any of these, they will be online. And my filled out versions will also be online, so if you think you missed a note. By all means, educational theory says that writing notes in class and writing notes after class is the best way to get it from here to here, where it needs to be. But, so there's our methane. So methane is made up of 4 sp3 hybrid orbitals. Each one of these then is an sp3 hybrid orbital. and the sp3 hybrid orbital looks like that. So that's how we explain why methane is symmetrical and tetrahedral. And that goes back to the Vesper theory. All right, but that's not the only carbon we can make. So then what do? We can say, I don't want to mix all three p orbitals. How about I just mix two? So again, I'm starting with this excited state. I mix those two, mix two of the three orbitals together. So now I make 3 sp2 hybrid orbitals. My Vesper theory tells me that if I have 3 balloons, what geometry should they have? Trigonal planar. So that's the shaded ones here. They're trigonal planar. And then what happens to the unpaired or unpopulated, unhybridized p orbital? It still has an upper and lower, it has the upper and lower dumbbell shape, and now it goes orthogonal or perpendicular to the other three. So that's what an sp2 hybridized carbon looks like. And so if I want to form a carbon-carbon double bond, let's say so if I wanted to form a CH2 double bonded to another CH2, then I take 2 sp2 hybridized carbons and I bond them together. So a couple things here. You can only put 1 electron in the molecules before you put them together, or in the atoms before you put them together. You can only put 1 electron in a hybridized orbital. So if I think about this carbon, it's going to have 1, 2, 3 of its 4 electrons in the hybrid orbital. And then where's the 4th one going to go? The 4th one's going to go into the P. Same thing over here. 1 unpaired, 1 unpaired, 1 unpaired, 1 unpaired. So we can only put 1 orbital, 1 electron into each of the hybrid orbitals. In the future, can I put a pair of electrons into this picture? Yes, but the pairs of electrons must always go into the hybrid orbital as well. So my rule here should be 1 electron, or the P for p orbitals, only 1 electron, never a pair. So hybrid orbitals can have 1 or a pair. We'll come to the pair later, maybe tomorrow. All right, so now if I'm forming my bonds, think of this as a Lewis dot structure now. I use 2 of the lone pairs to bond hydrogens on each of the 2 atoms. I'm going to go ahead and overlap those 2 to form my single bond. And that's going to form a single bond, which we are now going to call a sigma bond. So what's a sigma bond? It's when 2 orbitals overlap head to head. That's what sigma bonding is. Sigma bonding is the head-to-head overlap. Now, a sphere doesn't necessarily have a head, but all spherical orbitals form sigma bonds. Now, at this point, if I was drawing a Lewis structure, it would look like this. I have 2 unpaired electrons each on carbon. So in a Lewis dot structure, I would just go, oh, I'm pairing them up. Let's go a little bit deeper. What does that mean? That means I'm going to now overlap these p orbitals. P orbitals can only overlap side to side with each other. And what's that called? That's called pi bonding. So pi bonds occur when two p orbitals overlap side to side. So what does that molecule look like? I've got the little color-coded picture here. What we have is we have sigma bonds from the carbons to each of the hydrogens. We've got a sigma bond between the two carbons, and then we've got the two lobes of one pi bond. A pi bond is the top and bottom half, hold together. Those pair of electrons spend 50% of their time here, 50% of their time here, without ever ending up on the nodal plane. Again, that's quantum mechanics. So that whole thing, both lobes, is a single pi bond. So a pi bond then is the double or the triple bond. The single bond that holds the structure together is always a sigma bond. So if we relate that to back to what we just did, we arranged or rearranged pi bonds in resonance structures. We never rearrange sigma bonds. Because if you rearrange a sigma bond, the molecules fly apart. That also tells us that pi bonds are easier to break than sigma bonds. I break a pi bond with a minimal amount of energy. If I break the pi bond, or if I break the sigma bond, the molecule just disappears. So there's sp2. Here's a couple more viewpoints of that with the sigma and the pi bonds. Again, both of these, this is one pi bond. Okay. All right, so, and there's the third viewpoint. It's flat. Carbon-carbon double bond is flat. Or plane. All right, what if I only want to mix an S and a P? Same thing. Now what am I going to end up with? If I mix the S and the P, I'm going to end up with two hybrid orbitals. They're going to be linear because those two orbitals are going to push away from each other as far as possible. What's left over? Two unhybridized p orbitals. They're going to go on the x and y coordinates, or y and z coordinates, and they're just going to be normal lobes. So in that carbon, one electron here, one electron here, one electron in those two lobes, one electron in those two lobes. So still 4 electrons around the carbon, but every hybrid orbital gets an electron. And then the p orbitals get the other. And then I want to make a carbon-carbon triple bond. I'm going to do the same thing. I'm going to take my unhybridized, I'm going to take my hybrid orbitals with 1 electron each, pair those up, take the 2 vertical p orbitals, overlap them to form the first pi bond, take the 2 that are going. So one of these orbitals is going to be up and down in the plane, and the other one's going to be pointing towards you. And so the ones that are pointing towards and away from you, or in and out of the screen, that makes the second pi bond. So in a triple bond, we're going to end up with 2 pi's and a sigma. And so that's going to look like the structure on the right. The first pi bond, the second. Or kind of like, sort of like the bond. And so what this is going to mean for this class is we're going to do a lot of reactions of carbon-carbon double bonds. And then when we get to the triple bonds, I'm going to say, well, you know all the double bond reactions. Triple bonds just means you got 2. You can do 2 reactions for most everything. So the triple bonds are going to go fast. That'll be like the day before the final. So double and triple bonds are very similar in the way they react. But this is the way the hybridization, this is the way the hybridization fits the geometry. And so here's another viewpoint of that. So let me just introduce, what do we do with this information? Well, here's what we're going to do with that information, and we'll do this tomorrow. But I'm still going to introduce it now. What we need to do is, for the carbons, for a carbon-carbon bond, for carbon hydrogens, that all fits nicely into what I just kind of laid out. But what about non-carbon atoms? So if I said, hey, let's determine the geometry of each of the non-hydrogen atoms, so carbon and oxygen, and let's better yet sketch the orbital picture of how they're formed. The first thing I need to know is I need to know the hybridization, and I need to know the geometry, or both, well actually, and both, for this carbon and this oxygen. Now, what's going to be the Vesper geometry for the carbon, and what's going to be the Vesper geometry for the oxygen? Here. Let's deal with carbon first. So what's going to be the geometry, the Vesper geometry? And your Vesper geometries are linear, trigonal planar, or tetrahedral. And when I say Vesper geometry, this is unique to me. I always talk about both the lone pairs and the bonding pairs put together. So in other words, when I talk tomorrow about, when we talk more about this, I'm never going to use the word bent or seesaw or any of those, because those are what are actually called the molecular geometries. I'm always interested in the lone pairs, where they are. Okay. So here. Water. What's the geometry of the oxygen in water? Last question of the day. So, is it A, B, or C? Or D again if you don't know. Okay, let's see. I got 4 linears and 5 tetrahedrals. Uh-oh. So when this happens, when we have a nearly 50-50 split, and this will work better when we're sitting like maybe in groups, which maybe we'll do tomorrow. Start doing tomorrow, so that way you can kind of you can answer things, and we'll switch the groups around so that everybody will get a chance to work with everybody else. That's going to be disconcerting to those who only want to work with one person, but they'll make friends or not. When it's 50-50, what I usually do is I say talk to your neighbor for a minute And then I get my 1 minute egg timer out and slap it on the desk. And then we revote and we see, you say, I chose this, or I chose that. And so we do that. In this case, though, let me ask a different question. Is water polar? Or is it non-polar? Polar? Everybody agree water's polar? You don't look convinced. Polar? Well, on tap for tomorrow is polarity and intermolecular forces. How do we know if a molecule is polar? We're going to draw a bond dipole between the atoms, and if they cancel each other out, guess what happens? The molecule's nonpolar. So, if oxygen was really linear, if water was really linear, those two dipoles would cancel each other out and water would be nonpolar. But what is water? What kind of bond angle does it have? It's like 109. It's like 105.7, I think. So what we need to do is we need to basically be able to translate Vesper theory now with lone pairs. And so here's what we're going to say for oxygen. We're going to say, how many bonds and lone pairs does it have? 2 bonds, 2 lone pairs, total of 4. What are 4 lobes of electron density going to give us? Tetrahedral. And so the water is going to be tetrahedral. So the water question I usually ask, my job is, there is the answer that is there to ensnare you, right? The trick questions is that it's linear. It's not, because water is tetrahedral. Electron, it's tetrahedral in its electron pair geometry. It would be bent in its molecular geometry. But I'm interested in everything, bonds, okay? So that's what I'm interested in. And so now we could do methanol, which we'll do tomorrow, but we need to translate this. So first thing I'm going to need to know is I need to know the geometries. And from the geometries, I can figure out the hybridization. And from the hybridization, I can figure out how to sketch the molecules and then put the atoms together. And then we'll feed into the whole idea of why it has to be rho 3 or lower. And then we'll talk about polarity and intermolecular forces. And then we will complete it like a third of general chemistry. And like it better. Hopefully it's more review than anything else. So let's plan on this. Let's plan on by the end of Friday. This is going to be this week only, right? Because we're just getting into the swing of things, you and me. So by the end of the day on Friday, and end of the day means midnight, let's, all the chapter 1 problems in the text, I'll expect those to be done. Now, if you want to go, I would strongly encourage you not to wait until Friday to do that. I would strongly encourage you to go back today through the first half and refresh yourselves and do the problems on that. Some of which electronic configuration, I'm expecting that's going to be your review of electronic configurations. And then So by Friday, hopefully everything will be done in chapter 1, and we'll finish chapter 1 tomorrow. So if you want to, so I would encourage you again to read the second half, read the first half and then read the second half. There are my annotations in there. And then tomorrow I'll start with any questions on intermolecular forces, and we'll do some of that, but then we'll go back and do some of this as well. All right, so that's the way things are going to work. If you have any questions, you can stop by, except for 4. When am I not available today? Today I'm not available between 4 and like 5:30 because I have to do something for the new students that are coming in, scare the hell out of them so that it's a good cop, bad cop. Here's the core. How good are your academic skills? So somebody has to be the good cop and somebody has to be the bad cop. I think I'm sure be the bad cop today. So other than 4 to 5:30, I'm around. If you're not around, I will answer emails probably up till at least till 9:30 or so. If you get it at midnight, I probably won't respond. But if you have any questions, you feel free to ask. We can start with that tomorrow. I can email you back. I can write stuff. I have the ability to write videos and send them back to you. I'll probably put that in the discussion board. So if you want to, I'll open up the discussion board if you want to submit something to the discussion board. I don't know if you're used to using that very heavily at your school. I usually don't bother with it, but I will. So if you ask a question, we can throw it up there. But if you have any questions, by all means ask. And even if there's questions on problems from the book, feel free to ask on those. And feel free to tomorrow to bring them in and say, hey, I don't understand that question. We'll go over it. Remember, those are participation points. So the importance of them is you figuring out what the answer is, you learning that, because that'll come back. All right? And then I'll post all this stuff within a couple of hours, so if you needed to go back, you can.